Okay, so just briefly, let's talk about just remind ourselves what we did last time. Basically, we just drew some vectors, right, between of reference and current configuration. We wrote down some vector equations based on that, essentially, labeling Q minus X, okay? And then we did a Taylor, so this is just Q minus X, and written on the left-hand side, things in the current configuration, but on the right-hand side, everything is in the reference configuration, right? And then we did this Taylor expansion about the point Q equal to X. So if you recall, when you do a Taylor series expansion, you have to do it around a point, right? Often you do it around, X equal to 0 or something like that. But you have to do a Taylor series expansion about a point. So we do the Taylor series expansion. That leads to this equation in indicial notation, and we'll have more to talk about indicial notation today. Hopefully things will become a little more clear with respect to that. So again, that equation is repeated at the top. And then, simply by just doing the Taylor series expansion about the point Q minus X, we're looking at a local neighborhood of X, right? So we're assuming that what we're talking about is close to the point X, right? And then, so since we're talking about things that, Q minus X is a very small or infinitesimally small value, we just label Q minus X, right? So Q minus X in the current configuration we call D little x, like a differentially small vector, and Q minus X in the reference configuration we call D big X, differential small vector there, right? So since we're talking about things that are close to X, or small in the neighborhood of X, then the higher order terms we ignore, and that leads us ultimately to this equation that maps vectors in the reference configuration, D big X, into vectors in the current configuration, D little x, and that mapping is called a deformation gradient, okay? And I misspoke at the end of class last time. There's one advantage to me recording my lectures is if I take the time to listen to what I say, I catch myself saying stupid things. I think at the end of class last time I said that the deformation gradient is fully nonlinear. Well, that's not correct. In fact, by definition, it's a local linear approximation, right? Because we linearized the Taylor series expansion. We ignored the higher order terms, right? So there are continuum theories that include the higher order terms. Those would be often referred to as like higher order continuum theories is what they call them. Typically, or you see it a lot in like crystal plasticity modeling and other things. So the deformation gradient is a local linear approximation to the deformation. But what it does lead to, as we'll see today, is it leads to a nonlinear definition of strain. Right? That was what was in my head when I said it's fully nonlinear. So the definitions of strain that we will derive from the deformation gradient are nonlinear. Okay. The other thing, I used some indicial notation there, and then right here in this equation, I kind of switched back to matrix notation, and I will do that quite readily in this class, right? So I will switch between indicial notation and matrix equation basically when it's convenient, right? So you really need to be comfortable with both, and the indicial notation just takes a lot of practice. It's really powerful, a way of manipulating equations in continuum mechanics, and those of you who know me know that I'm sort of a coding or computer first guy, meaning like whenever I set out to tackle a problem, I tend to like go right to my computer, whether it's like symbolic algebra to derive equations just to avoid making mistakes. I'll use tools like SymPy and Python, or I'll use Mathematica or something like that. I'm almost always like, I go to my computer first. The one exception is when manipulating continuum mechanics equations, because that I know of, there's not a great package that does this indicial notation really well. There's some that have tried, but I've never ran across one that just blew my mind at how well it could do the simplifications and things that you can do with indicial notation. So whenever I'm sort of deriving continuum mechanics equations and working on field theories and stuff like that, I always use indicial notation just on a piece of paper and a pad, usually. So we'll see today, like, where some of the power comes from in the compactness. But yeah, so you need to be comfortable switching readily back and forth. There's one thing that I probably should have mentioned last time, and it's just with respect to our definition of vectors. I mentioned that we have, on the previous slide, I drew a coordinate system, and I said, that these are like x1, x2, x3. Those are the magnitude of the vector big X, right? But we also have unit vectors associated with that, right? So big X is, the magnitude of big X, if we wrote it out in vector notation, would be x1, and you might be more used to from physics or an undergraduate statics or class or dynamics or something, using like I, J, and K for unit vectors. So x2 j hat plus x3 k hat. Okay, in this class we're going to use just the symbol E for a unit vector. So, or in this case, it'll be E1 plus x2 E2 plus x3 E3. I'll try to always use the little caret on top to identify a unit vector, right? So a unit vector is just a vector that has a magnitude 1, right? And the reason we're going to use E1, E2, E3 in place of I, J, and K is because then it leads again into nice indicial notation, right? So I can basically rewrite this equation more compactly as the sum from 1 to 3 of x, I, EI, right? And of course, remember what I said, anytime you have a repeated indice in a term, it implies summation. And when we're doing the typical manipulations, then we just ignore the summation, right? So we can write this most compactly as xi EI, okay? So again, here's a direct one-to-one. Xi EI is just that, right? You see a repeated indice in your mind, you can expand it into a sum, okay? So along those same lines, what I'm about to do now is going to be a little bit painfully explicit, but in the literature a lot you'll see some abuse of notation, and I just want to make it clear here, right? So we have that equation up there, dx equals the Kronecker delta function plus partial ui partial xj times dx. And what I'm going to do is I'm going to write out all the components so you can see what that equation is in 3 dimensions, right? So we're going to assume that I and j go from 1 to 3. So we'll write out all the components of that and see what we have, okay? So the first thing, just again to help you, I'm going to write this as, all right, so we're going to assume I equals 1, right? Whenever you have a free indice, remember what I said last time? Whenever you have a free indice, that's an equation. When you ever have a repeated indice, that's a sum, okay? So we're going to write the equation, we're going to only fill in the terms for I equals 1 for the moment, right? So I'm going to say I equals 1, so that's dx1 equal to Kronecker delta function 1j dx j. Oh, I don't need the vector symbol there because it's a component, right? So that's Kronecker delta 1j, right? So again, this is like the sum over j, okay? Plus, again, there's the sum over j, partial u1 partial xj dxj, right? Now, remember what I said about the Kronecker delta function. Kronecker delta function is if I equals to j, it's 1, otherwise it's 0, right? So if you look at that first term, only when j is equal to 1 will that term be non-zero, right? So if j is equal to 1, then I have Kronecker delta function 1, 1 dx1, right? But Kronecker delta function 1, 1 is I equal to j, right? That's 1. Oops. So this is 1, right, plus this same term, all right? So with that in mind, now I'm going to write out all three equations, okay? So let's start over here. dx1 equal to d big X1 now I'm going to expand the sum and do it again for the next equation, right? So now I equals 2. All right. So, I mean, just this thing is the same thing, right, as that thing. These are just expanded out versions of that equation up there. So you can see where, I mean, just in that alone, there's power, right? Because I can write three big, long equations in one little compact equation with the indicial notation. Okay? So I want to take a little aside here. And again, this is getting after what you'll see in literature as an abuse of notation often. Let's just go back to calculus for a second. Okay, if I have a vector u, and I'm going to write out the components, u1, e1 plus u2, e2 plus u3, e3. Now, if you look up, if you went and opened your old calculus textbook and you looked up what the gradient, remember taking vector calculus, right? If you look, so you looked at, when gradient, in vector calculus, you looked at gradients and curls and divergences and things like that, right? So if we looked at what the gradient operator is, and just to be explicit, I'm going to put a big X here, meaning we're going to take derivatives with respect to big X in this gradient operator, right? So if I looked at what the gradient operator is for anything, that this kind of notation where I just have a parentheses and a dot means like whatever I'm going to stick in there, then this is what the operator is going to do, right? So no matter what I stick in there, then the definition of a gradient is this. That's straight out of calculus. If you looked up your calculus textbook, that's what it's going to give you for the gradient of something, okay? So with that, then let's take the gradient of u. So basically we're going to stick u, everywhere you see the dot, we're going to put u there, but we're going to write out all the components, okay? So the gradient with respect to big X of u is equal to E1 hat plus sorry, this is a little painful, but let's just get through it. Plus all right, well, we also have this notion of a dyad in mathematics, or like a better, more common name is a second order tensor. So if we have a second order tensor, A, it's defined as the sum over I, sum over J, AI, BI, BJ, EI, EJ. And so, kind of given that definition, what we'll do is then write A from this equation, or basically pull out the E's and write a matrix equation here for the components, right? And what that is, again, the gradient of u in matrix form So that's what the gradient of u is in matrix form. And anytime you take a gradient, right, if you know, it's a good way to sort of, when you're looking at math, I always just look at it and make sure that I have the same order on the right and left-hand side of any equation, right? So if I have scalars on the, you know, you can't have an equation that has scalars on one side and vectors on the other, or vice versa. So one little simple check I always do is just check the order of the terms on both sides of an equation, right? And one thing to remember is that anytime you have a gradient operator, you always go up an order, right? So if you take the gradient of a scalar, you get a vector. If you take the gradient of a vector, you get a second order tensor. If you take the gradient of a second order tensor, what do you get? A third order tensor. You take the gradient of a third order tensor, what do you get? A fourth order tensor, right? So you go up, right? All right. So just one last thing is, returning to these equations up here, what I'm going to do is I want to write these in sort of a vector notation. I'm going to run out of space. You know what? I don't think I need to write it all the way out to make my point. Okay, so if this is the gradient of u as defined from, yeah.
The last two elements will have x3.
X3 there, yeah. All right. If this is the gradient of u, what is this? That I know I didn't write it all out, but if you just look at the equations over there, I'm pulling out the partial derivative coefficients, right? So if this is the gradient of u, what is that? It's the transpose of the gradient of u, right? And so if you look back to this equation for the deformation gradient, you notice I wrote the transpose of the gradient of u, and that's why, right? Because using the technical mathematical definition of a gradient, what we derived is actually the transpose of the gradient of u, not the gradient of u. And I make a big deal about that because in literature all the time you'll see that the deformation gradient is I plus grad u. But it's not. It's I plus grad u transpose, right? And grad u, we call the displacement gradient. Okay. Yep.
In the previous page, like you said, that this thing is equal to this matrix, but shouldn't there be a multiplication somewhere? Like this here?
Where? Here?
The other one below?
Here?
Yeah.
Well, so what it should say is that a dyad or second order tensor is the ij bj term, is this thing, right? And so, because this would be a scalar, but this thing right here, this thing is a second order tensor, right? And so what I'm trying to do is I'm trying to write just the second order tensor. Yes, there would be the unit vectors over here too, right? Yeah. To write the whole equation. But yeah, just Okay, so that's, yeah, another question?
You bring in the E1 inside the equation, right?
Mm-hmm.
So E1 dot E2 should be 0, right? Like I dot J is 0. So is there a need to write the whole equation like that? Like when we do the divergence, the whole thing converts into scalar quantity.
When you take the divergence, you said,
Oh, sorry.
yeah, gradient. Yeah, no. The gradient is this, okay? This equation would lead to a scalar quantity once you summed up over all the terms. Yeah.
Yes.
But the gradient is this thing, right, by definition. Yeah.
But mathematically speaking, if you
Because we always, typically when we write it out in math form, we don't keep the unit vectors, right? You just would have the gradient, normally you would just say, typically you would just say the gradient operator is a vector, right? Partial x, partial x2, partial x3. By the way, anytime I write a vector symbol, like something with a hat over it, by default, I'm talking about a column vector. Yeah. I guess in this case, the thing there would be a scalar. That would result in that. If it was a vector, if the thing that you're taking the gradient of was a vector, then you would result in something like this, right? All right. So, just want to point out one more thing. So remember we had that little x, just going back to our potato, little x is equal to big X plus u of x, right? So if we take the derivative of both sides of that equation with respect to x, so we get so I'm taking the derivative of both sides of that equation. This thing reduces to the Kronecker delta function. So what's the right-hand side here? We called it something earlier. Deformation gradient, right? So this thing is Fij, which means evidently that what is over here on the left is also Fij. So that just gives us another equation for what Fij is. So I'll just write Fij is equal to partial xi, partial xj. Right? And, just to be explicit, we need to understand that xi is a function of x1, x2, and x3. Right? Otherwise, it doesn't really make sense to try to take a derivative of something, right, with respect to big X. So that just gives us another definition of the deformation gradient. Right? Yes, it's I plus grad U transpose, or this might be useful, as we'll see later. Okay. Now,